Hi guys, this is Dr. Gonzalez here, and in this video I'm going to go over the Introduction to T-Tests Part 2. And I'm going to start by reviewing where we were in the last video and where we stopped in the process of calculating a T-test by hand, and then where we're going to go from there. So if you have your notes printed out, that would be great, and let's get started here. So last time we had calculated your first T-test by hand. We stopped on step 3 of the steps of the null hypothesis testing procedures. We're going to continue today and learn how to determine if your results were significant or not. Now, previously, we had already defined our null and our alternative hypothesis for the research question we were talking about. We were talking about a situation where we were looking at sleep duration and electronic use, and we had two groups. One group was going to use electronics before bed and the other group was not. So our null hypothesis is going to say that there is no difference between the mean of group 1 and the mean of group 2. Our alternative hypothesis is going to say that the mean of group 1 is not equal to the mean of group 2. And you'll notice that that is a two-tailed hypothesis here. I have not put the stipulation that I'm expecting to see an improvement in sleep duration. I'm just leaving it at two tails right here for the purposes of learning. So we also determined last time that we're using a t-statistic because we have a single factor but a two-level design, and this is an independent sample, so we are using an independent samples t-test. That's what we calculated in the last video. We did that by hand. And just to recall, a t-statistic is just simply the variance between groups divided by the variance within groups. Your numerator has the differences between the means of the group, and that's divided by the pooled variance divided by n, added to the pooled variance divided by n, and then taking the square root of that value, and then dividing your mean difference by that square root. You've got to remember that you calculate the means for both samples. You find the sample size for both samples. We then calculated our pooled variance. And in order to do that, we needed to calculate the sum of squares, and we needed our degrees of freedom for both samples. We came up with a t-statistic of t is equal to 2.934, and our degrees of freedom was 18. That's going to be useful in a moment when we get to talking about how we're going to make a decision and how we're going to set our critical values. Remember, pooled variance is these formulas that we went over right here, the sums of squares of group 1 plus the sums of squares of group 2 divided by the degrees of freedom of 1 plus degrees of freedom of 2. That was 9 plus 9 give you 18 here, and then up at the top we had a lot of different variables that I can't remember off the top of my head here, but we calculated our t to be 2.934, and our degrees of freedom is 18. So if you're given the variance, you insert that into s squared. If you're given the standard deviation, you square the standard deviation and insert that into s squared. And if you're given the raw data, you would need to go back and calculate your variance and actually go back and insert that into s squared. There's your last bit of your calculation, right? And again, we would say if you're given the variance, insert that where s squared was. If you're given the standard deviation, square it and then put it in the pooled variance. And then if you're given the raw data, you have to calculate the variance and then insert it into the pooled variance. But in any case, you're going to come up with a t is equal to 2.934. I hope by walking through this, you've seen that calculating one of these by hand is rather time consuming. This was also a distribution of participants that was only a total of 20 participants. So if you're having to do all of those sums of squares for 100 or 200 participants, it can get very nasty very quickly. So that's why we have wonderful programs like Jamovi and JASP and SPSS, and even Excel can do this for you. So where were we in our steps of the NHST? We are at the step where we state our significance or alpha level. And normally that is going to be done before we do that statistic that we calculated. And it's done that way because we want to prevent p-hacking, and we'll get into that later in the course about what that is. We basically don't want researchers to start messing around with their alpha level so that they go fishing in their data in order to find a significant result. All right, so significant testing is part of our hypothesis testing procedure, and it's a formal process that we use to compare our observed data with a previous hypothesis. And when we go to actually do our comparison, we're interested in p-values. And that p in p-value stands for probability. So a p-value is the probability of obtaining the result that you got if your null is actually true. Because remember, we assume a pessimist view that there is no difference between means. So if we assume that there is a true null, what was the probability of actually getting the results that we got? So when you have a lower p-value, you are more confident that you could replicate your results. Most standard researchers use a p-value of either 0.05 or 0.01, and that would be written like it is right here. P is less than 0.05 or P is less than 0.01. So a p-value of 0.05 means that there's a 5% chance that there was no real significant difference between your means. You can also see that if you have a p-value of 0.01, you're making your decision even stricter because you're now saying there's only a 0.01 there. There's a 1% chance that there was no real significant difference between your means. I have a couple of extra videos that are posted in Canvas that are from YouTube. They're not videos that I made, but they're going into the topic of p-values because I feel every year the need to really emphasize how you make your decision, because people tend to get this mixed up when we're talking about how to calculate something by hand versus how to calculate it in Jamovi. So when we talk about something being significant, we have a value for the statistic and it has a corresponding p-value. A significant result, a significant t-test score or t-score, is going to have a corresponding p-value that is less than your alpha level, okay? And that kind of goes in contrary to what we normally think of when we think of something being significant, quote, right? We're looking for a lower p-value, less than 0.05, that indicates significance. Now, it's a little different when we talk about the critical value of the actual t-statistic. So hang on to your horse as we go into the next part here. So we already established that that p-value of 0.05 means there's a 5% chance that there is no real significant difference between your two means. So if we take probability and we take that 0.5% and we divide it into two portions, it would look like this on a distribution. Now, it's divided into two portions because our particular research question was two-tailed. We were not looking at a direction for our hypothesis. So we could say the mean was either significantly greater than or the mean was significantly less than. And now there are corresponding t-values that are going to mark these critical regions. And by critical regions, I'm referring to the area under the curve right here and the area under the curve right there. Okay? So we've briefly touched on this in previous chapters. We talked about type 1 and type 2 error. I'm just bringing this up again because they are both related to alpha level. They're also related to internal and external validity. So type 1 error is when you reject a null hypothesis when it was actually true, okay? So that is a false positive. You said there was an effect, but in reality there wasn't. So you claimed something was effective or there was a significant difference between two groups, but in reality that significance was not there. And the contrary of that is type 2 error, and that's when we reject the alternative hypothesis when it was actually in fact true. So you had a false negative. You claimed there was no effect of variable X on variable Y, but in reality, there was an effect there. And for whatever reason, you did not catch it. Therefore, that is type 2 error. Now, if we plotted out all the possibilities for a p-value and put them on a scale like we do here, you would see that as you reduce your alpha, as you get very critical with the actual quantity that your probability could be, you are actually getting stronger in your evidence that something was significantly different. So down here at 0.99% of a p-value, this is not significant at all. There's absolutely no evidence to show that your means were different. And as we move along, we're going to jump really big here from 0.99. You're jumping considerably to 0.10. There's still no evidence, and it's not significant because the largest value that we recognize as a standard p-value is 0.05. And once we reach that, you can see that over here to the right-hand side, that's where our critical value would be from 0.5 on if it was significant. Now, if I reduce that alpha level even further and go to p is equal to 0.01, I've effectively cut what was my possibility into half, and I've made it even stricter as far as determining that significance of my results. So alpha level is that threshold that you set to determine if your p-value is low enough to reject that null hypothesis. The p-value is based on your t-score, right? The most common level is 0.05. You might set the alpha lower if there are more consequences to an alternative hypothesis being the null being rejected, right? When we reject the null, we claim the alternative is true. So if I'm doing a clinical trial on a medication or a treatment for something like cancer, I really want those alpha levels to be very small, because if I claim that there is a significant difference or a treatment effect, I want to be very sure that I am not putting out a false positive, right? So in the most recent years in psychology, it's been the standard to set a lower alpha level because it is a more there are greater consequences to things as we evaluate different aspects of science. So where are we in the steps of our hypothesis testing procedure? We are right now on the stating your significance level. And what that is going to help us do is make a determination. Do we reject the null? Do we reject that null hypothesis at 0.05 or at 0.01? We're going to go with 0.05 because that is the standard. Next, we're going to move into calculating the degrees of freedom. And this is going to be important because you need to know the degrees of freedom in order to determine what your critical values are for your t-statistic. All right. Now, when we're doing an independent samples t-test, like we were in the example, our degrees of freedom is equal to n minus 2. And that is the n of the first group minus 1 plus the n of the second group minus 1. So it's your total, which is n minus 2. So we had 10 and 10. So 10 minus, why is this thing going on its own? Sorry, I don't know why that was doing that, but 10 minus 10 gives you 1. 10 minus 1 gives you 9. 9 plus 9 gives you 18. So our degrees of freedom is going to be 18. So now we're going to use that information to state our decision rule and to select our critical values for our t-test. So in most statistic books, you have a t-table that is published in the back. And you'll notice that these t-tables have what's called a cumulative probability, and then they have one tail and two tails. Remember, we're dealing with two tails right here. On the y-axis, it's going to list the degrees of freedom, okay? And then you're going to have across there a section that you select based on whether or not you are dealing with a one-tailed or a two-tailed hypothesis. So to find the critical value over here in this table, you need to know your degrees of freedom, you need to know your p-value, and you need to know if you are dealing with a one-tailed or a two-tailed hypothesis. So how do you know if it's one-tailed or two-tailed? That depends on the research question that you're asking. If you are asking if one mean is more or less than, notice the word or, that would be one-tailed. If you're just simply stating that the means are different, that would be two-tailed. So next, you're going to decide your level of significance. You're going to read down the corresponding column till you find the degrees of freedom that you've already calculated, and you're going to find a value in that table. And that value is the minimum value that the t must be in order to be significant. So it's the minimum or greater for the t value. Now, for p values, it's going to be less than the level that you have established. And we'll talk a little bit more about that in just a moment. So why is this important, and how does it relate to sample size? So you already know that every time you increase a sample size, you get one step closer to the actual population number, right? So a larger sample makes it much easier for you to detect a difference. And remember, degrees of freedom is always n minus 2. N is the total from group 1 and group 2 added together, and then you subtract 2 from it. So over here, there's an image, and it tells me that when you've got two groups of 5, so 5 and 5, t is equal to 2.0, p is equal to 0.04. So I calculate a t statistic, and I get 2, and that is significant at the 0.05 level because p is equal to 0.04. It is less than the 0.05 that I've established. But if I've got two groups of 10, when you've got the same t value, now my p is still significant. It's still less than 0.05, but you notice it went down by 1 whole percentage point. So the larger your sample size, the easier it is for you to detect a difference. So what are you going to do? You are going to look at that table. I will publish a copy of this table in Canvas, but there is also one, you can find them online. Just Google a t-table. We have already set our alpha at 0.05. We have already calculated our t statistic, and we got t is equal to 2.934. Our degrees of freedom is 18. I don't know why it says 40 there. That is not correct. So I don't know why that's there. But take what we just did on the other side. This should be 18, guys, not 40. But you're going to read this chart based on that information. So we've got our t value, 2.934. Degrees of freedom is 18. We need to find the critical value. So we're going to come over here and we're going to use a two-tailed, and we're going to go to 0.05 for our alpha level. So you can draw a line through this until you stop right there. And then you're going to go down until you get to your degrees of freedom. And our degrees of freedom was 18. So our critical value, sorry, this is not very easy to do. Our critical value is 2.101. That means as long as your t value is greater than 2.101, you are going to reject the null. And it's a plus or minus deal, guys. We're looking at a two-tailed particular hypothesis here. So it is going to actually be a plus or minus. So 2.934 is greater than 2.101. If my means had a difference that indicated a decrease for my treatment, I would need a number that was less than negative 2.101, but that's not the case here. We're dealing with a positive number. Our t-score was 2.934. That is greater than our criteria that we set, so we're going to reject the null. Now, be careful. When you do this in Jamovi, you are not going to focus on what the t statistic is. You're going to focus on your p-value, okay? So in your Graviter book, which is the chapters that I have uploaded for you, it's not a required textbook for purchase. I did include chapters 6, 7, and 8 in a link. You could see a chart with the t-values, or you can look at the chart I'm going to put in Canvas, or you can Google it. But basically what it is doing is it is taking that critical value that we found, which was plus or minus 2.101, and that is at a p is equal to 0.05 alpha level for a two-tailed test. Remember, two-tailed divides our probability into two sides, and we bind our critical regions with these markers. Anything that falls in here, we fail to reject. Anything that falls in here, we reject the null, and we do state that there was a statistically significant difference between our two means. So remember, your null hypothesis, there's no difference. Your alternative hypothesis, there was a difference. So when your t-value is outside of your critical t boundaries, you have a significant result, and you're going to reject the null because you do have evidence that there was a significant difference between your two values. If your t-value is inside the bounds, right, in that larger portion of the distribution, it's not significant, and you fail to reject because you didn't have any evidence that there was a significant difference between the two group means. So here's where we found our critical values. I just kind of overlapped it here with, sorry, I've lost my mouse again. I just kind of overlapped it with what we were talking about on that last page. I put the t equals 2.934 and your degrees of freedom of 18, just so you could see where that falls. If my critical value, I can't do this, I've got to switch this back to a laser pointer, sorry guys. So if my critical value is positive 2.101 and I got 2.934, that falls somewhere over here under the curve in the portion where I would state that I would reject the null, because there is a significant difference between my two groups. I don't know why I put that again. It's the same thing we just went over on the other page. I just did it twice. So where are we? We are now at the portion where we state our results. What we are looking at is a t-value of 2.934. It was within our 95% critical value accepted range. So our t-value was significant, and we did reject our null hypothesis. So we're going to take that and we're going to state it in a conclusion. And your conclusion has to be stated in APA format. So there's a specific way to write it, and this is the actual format for it. You can find this format in your APA style guide. But what it basically boils down to is you say, on average, participants, and you would say in group 1 or in the electronic device use group, right? They had a mean of X and a standard deviation of X. You're going to input those mean and standard deviation from your calculations, and you're going to compare that to, and you list to the second group, right? And you're going to put their mean and their standard deviation there. Then you would calculate the difference. You would say this difference, etc., was or was not significant, and then you report your statistic. You would say T, and then you would substitute your degrees of freedom. In our case, it was 18, is equal to, and you put your T statistic, and then you report whether P was greater than or less than 0.05, or if you use Jamovi to calculate it, it's going to give you an actual p-value. It's not going to give you a greater than or a less than unless it's super, super small. And in that case, you would just write out whatever it tells you. And I'll show you what I mean by that in a few moments. So this is a write-up. Right here it says, on average, participants in the no electronics group had longer sleep duration. They had a mean sleep duration of 8.13 with a standard deviation of 1.27. Compared to those in the electronics group. Those who were allowed to use electronics before bed had a mean duration of sleep of 6.79 hours with a standard deviation of 0.687. And that difference, 1.34, was statistically significant with a t-value of 18 degrees of freedom of 2.934, which corresponds to a p-level of less than 0.05. All right, let's transition into a paired samples t-test. Again, I remind you that the 4th video in my video series is going to go over how to run all of these tests in Jamovi. It's going to review all of the different tests, the assumptions, what you would do with the data, how it would need to look inside of a spreadsheet, and then it will walk you through. So no worries. So a paired samples t-test, this is an example here. It would compare two means based on related data. So maybe I've got repeated measures or a matched sample. Remember, we call these situations within subjects designs, dependent samples, or repeated measures, just depending on what we are studying for our research question. So one of the things we're looking at is this possible question here. I want to know if incremental studying is more effective than cramming. So I've got 10 participants, and my manipulation of my variable comes in the type of studying. So what I'm going to do is I'm going to take my 10 participants and I'm going to ask them to use 2 different study techniques across 2 weeks. During week A, they're going to do what's called incremental studying, and that means participants are going to study material for 15 minutes each day for the whole week. So they're going to get 7 days of these 15-minute blocks. They're going to study in increments. And I'm going to compare that to week B, where the same participants are going to come in and they're going to cram. And this means they're going to be asked to study material for 105 minutes only the night before they are assessed. And they're going to be measured on their performance on a quiz that's related to the week's specific material. So there are 2 different quizzes, but they're going to be matched appropriately in their content and challenge, because we'd have to keep that consistent across my groups in order to validly use this particular design. So here's what it looks like in week 1. You have 5 participants studying for 15 minutes times all of the rest of them. These guys over here, they do nothing, and that participant over here, 5 participants are going to study for 105 minutes. So this is day 1, day 2, day 3, day 4, day 5, day 6, day 7. Then all participants take the same quiz. Then I flip. If they were in group 1 right here in the second week, they're going to do nothing until day 7. That's when they cram. And then the other group is going to actually study in increments. So then I'm going to calculate a total quiz score for their quizzes. And I'm going to have a score for an incremental studying and a score for after they cram. So this is just a chart that would show you what this might look like. These are our scores. You'll see that each participant has 2 scores. One score correlates to incremental studying and the other one correlates to cramming. By correlate, I mean it just corresponds to. It's not correlated with anything. So for a paired samples t-test, I'm going to use what's called X bar sub D, which is the mean difference. I'm going to do my standard deviation of differences, and I'm going to need to know N, which is the number of pairs. And my degrees of freedom are going to be N minus 1. So I would calculate this out, and seriously, do you want to sit here and do this by hand again? Because what we would have to do is calculate that X bar sub D, which is the difference between this one and this one. So the calculated difference, 19 minus 17, gives me 2. And you'll see right here I have a -1. So how is that going to be fixed? Well, I'm not going to make you go through this by hand again. I'm going to go ahead and skip to some Jamovi output so you can see what we would actually do in that situation. So before we get to the output, you need to make sure that you know what your significance level is. And this is where we are in this particular example. We're going to use P is less than 0.05 again, and that means our value is going to be less than 0.05 to be significant. That's our P value. We're going to leave it two-tailed, so we're going to divide that P into 2 segments, one on each side of the distribution. And we're going to reject the null if it falls down here or over here, and we're going to fail to reject if it falls in this 95% range. So what I did was I ran this in Jamovi and I came up with a paired samples t-test output. And I'm comparing incremental studying with cramming. I calculated the student's T. My T statistic was 3.71 with 9 degrees of freedom. And this says my P level is 0.005. And I have my mean difference and the standard error of the difference. So I'm pulling this significance level, that alpha. I've already established that. We've done our degrees of freedom, and we're going to pull that straight from these results here. Okay. So you're not going to use a table with critical values, because when you do this in Jamovi, your rule is based on your p-value. If your p-value is less than 0.05, you reject the null. And if your p-value is greater than 0.05, you actually fail to reject the null, which is also called retaining. So if that T statistic fell in one of these outer regions, that would be either negative, or if it falls between negative 2.262 to positive 2.262, if it's outside that range, so if it's over here or over here, we reject. And our T was 3.6, so it definitely falls over here, right? Because if this line right here is 2.262, 3.6 is greater, so it's somewhere over here in this region. So what do? Reject or accept? You're going to notice it's outside that extreme range, so we reject our null. There's your 2.262. Ours is 3.6, so 3.6 is somewhere over here. We reject the null. There was a significant difference between cramming and incremental studying. So there's the full-on results. I included descriptive statistics. When I walk you through these in Jamovi, I will show you how to get those descriptives. But you've got your statistic again, your degrees of freedom, your p-value, the mean difference, and then I've got my means for my scores for each of my conditions. Incremental studying had a mean score of 17.6, and cramming had a mean score of 15.5. You can see your median, your standard deviation, your standard error. So you can pull that over and look and find your stat there and your p-value. And based on that, I can determine that the results were significant. There was a significant difference between the means of these two study methods, because the p-value associated with my statistic was less than 0.05. So where are we? We're stating the results now. You don't have to use a table because we're doing this in Jamovi. We already know our rule. Our rule is that it is P is less than 0.05. We reject. We've already made that decision. So there's a significant difference. Now we're going to write it up. And this is what it will look like. We would say, on average, when participants used incremental studying, they performed better on a quiz. And then we report the mean of their score and standard deviation. Mean is 17.6, standard deviation is 2.37. And we compare that to when they crammed, which was mean is equal to 15.5, standard deviation of 2.01. There was a difference of 2.1 points on the quizzes, right? And that was significant with T of 9 degrees of freedom. There's your degrees of freedom right there. The T was equal to 3.6. And your P was equal to 0.0005, which is less than 0.05, which is why you decided to reject the null. So I hope you can see, seriously, who would want to sit there and work all of that out by hand? Like I said earlier, it is important for you to know the basics. So please go back and study how to look at that independent samples t-test by hand, because it's important to understand, especially that pooled variance. Or what does M1 minus M2 mean? And you should recognize that M1 minus M2 means the difference in means. So where are we going next? So next you're going to go into the fourth and final video. This fourth and final video is going to be an in-depth walkthrough of the different varieties of t-tests, and it's going to specifically apply to how to calculate them, interpret them, and write them up based off of Jamovi's output. And that's very important because that's what your learning check, part of your learning check, and your weekly assignment are going to be based on. And of course, this info will be covered on your final exam. If you have questions, please reach out. Contact me if you need office hours, and good luck.